Marini. Okay, just to introduce you, Professor Marini. Professor Marini is was a student, and he in L'Aquila University. He got his master's degree in 2008, and then he was as a PhD in the United Kingdom in the University of Bath. Where he got the PhD degree in 2011. Then he was a postdoc in Max Planck Institute in Erlangen in Germany, and then he was also in Spain as a postdoc until 2017. In the meantime, he got 2 times the Marie Curie. That is an award for young people that is very important and is very prestigious in Europe. And also he got the Rita Levi-Montalcini assistant postdoctoral fellowship that allow him to come back in Italy. I wanted to say that Andrea had many possibilities to go somewhere else also, but he decided to came back in L'Aquila. That is the city where he grew up and started his career. And now, since November 2020, Andrea is an assistant professor at the physical and chemical department of the University of L'Aquila. Today, he will speak us about the chirality in science and technology. And there is also the title is more complex because he will is through the looking glass and what Alice found here. So it will be very interesting to hear this talk from Andrea, and so I will let him to speak. Okay, thanks.
Thank you, Francesco, for the introduction. So I'm trying to share my screen here. Let's see if I can make it. Yeah. Do you see my screen?
Yes, we see it, but not in full screen mode.
Okay.
Okay, now it's okay.
Okay, so thank you, Francesco, for the introduction. So yes, today I will talk to you about chirality and its role in science and technology. And to talk about this topic, we will take together a brief journey through the reference object of chirality, which is the mirror. Okay. So the mirror, since long time, has constituted an artistic, literary, and cinematographic topic. The most famous reference for this, of course, are the novels of Lewis Carroll, Alice in Wonderland, and Through the Looking Glass and What Alice Found There. So, apart from literature, the mirror has constituted a subject for several arts, as in particular paintings and nowadays cinema. Mainly because the mirror is related to several concepts. For example, beauty, fear, truth, but also deceit. So as you can see in these paintings from Caravaggio and Edward Burne-Jones, beauty is a typical theme of mirror, but mirrors do not talk only about beauty. For example, they talk about fear, anxiety, like in this painting from Carbriullos. And more recently, in modern cinema, they are more related to truth and deceit. For example, in Wild Strawberries from Ingmar Bergman, Isaac, when he looks into the mirror, he finds out he's old and he's gonna die soon. While the leading character of The Apartment of Billy Wilder, when he watches the broken mirror, he finds out that he was deceived by his lot. And so there are all these thematics associated to mirrors, also in arts. But since the 20th century, with the advent of psychology, the mirror is associated mainly to the theme of the double. So the ones expert in literature will know more about this, more than us scientists. So basically, this is particularly relevant in cinema, where the theme of the double has been picked up by several recent TV series and also movies. So, for example, in Twin Peaks, Agent Cooper, when he smashes the mirror, he finds out Bob, the evil spirit of Twin Peaks. Also in Dark, the leading character, Mikhail, is lost in alternative universes. So, why the mirror? One can ask himself why the mirror somehow transmits us this sense of anxiety or weirdness. So one possible explanation is that mirrors do not reflect the world surrounding them as it is, but they do reflect a world with opposite chirality, which is what we're going to talk briefly today. So in order to understand this, we should take a brief look at how mirrors work. So if you take a mirror and place on top of the mirror a light source, for example, a lamp, then the light source will spread light rays around itself. And these rays will impinge on the surface of the observer, in this example, this girl. So once the rays hit the body of the observer, they get reflected and impinge on the mirror. Because of the laws of reflection by metallic surfaces, the light rays get reflected with a reflection angle with respect to the normal of the mirror, which coincides with the impinging angle. But because of this, the brain of the observer gets deceived, because for the observer, it's like the ray comes from the other side of the mirror where the image is formed through this mechanism. So one can think that the image through the mirror coincides with the observer, but if you take a closer look, it doesn't coincide really, because, for example, in this case, while the hair of the observer are on the left, in the image, they are on the right side of the observer. So there are several objects in nature that are not chiral, meaning that they are symmetric under reflection. For example, this pair of glasses is symmetric by reflection under this plane of symmetry, meaning that every point of the object, for every point of the object, there's another point in the other side of the mirror at the same distance, in this case with the same color and with the same shape. So apart from objects, reflection symmetry is present in nature. For example, our face is symmetric with respect to our axis, also in the animal world. For example, this butterfly and this crab, is it a crab? I don't know. But not all the shapes and figures in nature surrounding us are symmetric by reflection. So the first definition of chirality was given by Lord Kelvin in the early 20th century. And basically the definition of chirality is associated to hands. Why is that? It's because a chiral object, it's an object that once it's reflected through the mirror, the image conceptualized through the mirror, because it's an image in our brain, it's not a real image, cannot be superimposed with the object itself. So this is exactly the case of our hands. So the mirror image of our right hand, for example, is exactly the left hand. So one could think to superimpose the hands in this way, but if you do that, this is a trick, because if you take a closer look, when you superimpose them like this, the palm of this left hand does not correspond to the back of the right hand. So hands are intrinsically chiral. And indeed, the word chirality comes from the Greek, comes from hand. Okay, the etymology is hand. So there are several objects in nature that are chiral. In particular, all the amino acids that compose proteins that give birth to life, they're all chiral. And in particular, they are left-handed. The same is for DNA and also several plants surrounding us. For example, this is an example of aloe vera. And as you can see, this is not symmetric with respect to this axis, or same as this axis. So the same happens not only for plants, but there are also some animals and, for example, bacteria or viruses that are chiral. So chirality does not happen only for shapes in the universe, but it's really associated to basic physical mechanisms. And the most so the case where chirality is mostly prominent is the case of CP violation. So if you consider an atom composed of neutrons and protons, it can happen the so-called beta decay, which means that a neutron can decay in three particles: a proton, an electron, and a neutrino. So during this decay, one would expect that the emitted neutrinos wouldn't have a preferential left-handed or right-handed nature. But what is observed is that the emitted neutrinos by beta decay are always left-handed. So somehow the chiral symmetry of our universe is broken. And this fact has bothered theoretical physicists for a long time, over the last decades. So one solution to restore symmetry would come. So there have been several proposals, theoretical proposals to restore symmetry. One of this is that there exists a mirror universe, completely superimposed to our universe, where the matter inside this universe interacts only weakly with our universe, and as in particular by feeble interactions and gravity. So this theory has been proposed by Professor Berejani from the Department of Physical and Chemical Sciences, and it could lead to the explanation of dark matter in our universe. And at the moment, the experiment CMS is trying to verify this hypothesis, among others, of course. So the chirality is much more present. One could think that the beta decay is kind of far from our daily experience. But the chirality shows up in several mechanisms of our daily life. For example, light. The light we observe every day is chiral. So there are several elements of chirality in light. The simplest ones are the polarizations of light. So to understand polarization, you should recall that light is approximated as a ray in the geometrical description of light, But truly, light is an electromagnetic wave, meaning it's an oscillation of electric and magnetic fields over space and time. So in this GIF, you can see a left-handed polarized plane wave of radiation, and the vectors you observe, the vector you observe is the electric field. So as you can see, while light propagates over this direction, in this plane, the electric field rotates in clockwise direction. So there exists other combinations of oscillations of electric fields in electromagnetic waves, as in particular the opposite polarization, meaning following the right hand. So when light propagates over this direction, the electric field can oscillate also in the other direction. Okay. So this clockwise or anti-clockwise rotation of the electric field is associated to the concept of polarization, meaning that this electromagnetic wave carries with itself an angular momentum associated to the vector nature of the radiation. So there are several other chiral properties of light. One of these is that it's not only the polarization of light that can be chiral, but also the shape. So as I said, the electromagnetic field is it's basically a vector field. So it's a vector with an amplitude and a direction and a verse in this place over space and time. So there is a chirality also associated. So as you can see in this figure, since the electric field is provided by an oscillation, the amplitude will be constituted by a modulus and a phase. So there exists a class of optical beams with some intensity pattern like this, which can look normal, but where the phase changes around the propagation axis. And the rate at which this phase spins around the propagation axis is called the topological charge. Okay? So these two are the simplest chiral properties of light and can be exploited for several technological applications. One of that is, of course, optical communications. So in optical communications nowadays, scientists are trying to exploit not only the polarization, but also the optical vortices I mentioned before to increase the bandwidth of optical communications. But also all these optical vortices can be exploited for quantum information, which nowadays is revolutionizing information technology, as in particular quantum computing and quantum communication and quantum key distribution, enabling to send messages encrypted. So it's quantum cryptography. And also, optical vortices play a leading role in the development of optical tweezers, which have enabled several applications like laser cooling and development of physics of cold atoms and condensates. So all these applications I mentioned here have led to several Nobel Prizes over the last decades. The last one in chronological order is the one given to Professor Arthur Ashkin in 2017 for optical tweezers. But also, the chirality of light can be exploited for nanophotonics, which while I study in my daily research. So I will talk briefly about nanophotonics. So the research we carry out here at the University of L'Aquila is carried out in collaboration with several other universities from Europe, in particular the CNR unit here in L'Aquila, in particular with Dr. Alessandro Ciattoni, the CNR unit of the Institute of Complex Systems from Rome, particularly Professor Claudio Conti. We collaborate with Politecnico di Milano, especially with Giulio Cerullo, and with ICFO, the Institute of Photonic Sciences in Barcelona, with Professor Javier Sedabajo, Jens Diert, and Frank Coppens, and with Aalto University in Finland. So basically, what is nanophotonics? It consists of exploiting the properties of a radiation and also the chirality of radiation, among other properties, to confine light in tiny regions of space well below the so-called diffraction limit. So basically, if you produce a light wave with a laser or with lamps, you can see that well because lamps are incoherent sources of radiation. So without going technical, if you have an LED with a spot, if you look far from the LED, its spot, you will see that it increases over propagation. So you can try to focus the spot of an LED, and what you will observe is that the spot will shrink and shrink until it reaches a size which is comparable to the wavelength of the radiation, and then it will diffract again. So nanophotonics consists of shrinking down the dimensions of confinement of radiation. So this can be done by the use of new 2D materials, particularly graphene, but also with metallic structures. So research in nanophotonics here at Univaq consists exactly of studying the optical properties of graphene for several applications, and also monolayer transition metal chalcogenides and other kind of 2D materials. And we're interested in metals and plasmas and how they can influence the propagation of light, and also the so-called epsilon zero materials. These are basically materials with a refractive index very close to zero, and they are very exciting because it is possible to freeze light waves inside these materials and just make some light traps. So all these properties, interesting properties of nanophotonics, as I've said, come from the fact that these 2D materials enable a tight confinement of light with a wavelength an effective wavelength much smaller than the wavelength in vacuum, which is not possible. So apart from nanophotonics, the chirality is important in several other aspects of our daily life. In particular, if you go to the microscopic world, most of the molecules are chiral. For example, in this case of propylene oxide, which has this shape, you can see that it can appear in two distinct geometries, where the atoms composing the molecules are exactly the same, but they are arranged in a configuration which cannot be superimposed to its mirror image. So these two possible realizations of propylene oxide are called enantiomers, meaning exactly what I said, molecular realization composed of the same atoms but disposed in opposite chiral geometries. So one could think that enantiomers, because they are composed of the same atoms, in particular these atoms are at the same distance, the bonds between the atoms are exactly the same, so one would expect that opposite enantiomers, they behave identically in chemical and physical reactions. But this is not true. In particular, enantiomers show several marked differences in biotoxicity, pharmacokinetics, and pharmacodynamics. An infamous example relevant to this context is the one provided by thalidomide. So this was a drug that was produced by the German company Grunenthal, and it was marketed from 1956 to 1961 as a drug to treat anxiety and insomnia. And among the other, so this drug was sold also to pregnant women because they suffered from insomnia. So what was observed over the years, it was that while the enantiomer of the thalidomide indeed was sedative and it was useful to treat anxiety and insomnia, its S isomer was teratogenic. So this led to a medical disaster that is among the largest ones in recent history. In particular, it led to thousands of miscarriages and more than 10,000 children born with hypophilia and AD. So fortunately, science and technology have moved forward, and today thalidomide is safely used to treat multiple myeloma, and most of the top-selling drugs around the world are sold and administered as single enantiomers, producing the desired physiological activity and trying to minimize side effects produced by the opposite enantiomer. So the techniques that have enabled such an advancement are the liquid chromatography, so machines like this, and in particular polarimetry. So the particular case of polarimetry, as you can see, it deals with light. And how does it work? It's basically you produce light by a light source. You insert a polarizer, so you polarize light in one direction, and you shine it through your pharmaceutical sample. And what you observe, since this sample is chiral, it will lead to a rotation of the polarization of light. And from the angle of rotation, called Faraday rotation, it's possible to understand the imbalance between the opposite enantiomers. But nowadays, as technologies are moving forward and other techniques are exploited to measure the chirality of samples, as in particular circular decoys, which is explained in this picture. So this does not work in terms of the optical rotation, the Faraday rotation, circular birefringence, but it works with absorption. So basically, you shine light over the sample with two opposite polarizations, one right-handed and one left-handed, and you measure the amount of absorbed radiation by the two opposite polarizations. And from this imbalance, called differential absorption, you can retrieve the enantiomeric concentration of the sample. So these innovative techniques enable innovative solutions for personalized medicine and in situ treatment, meaning that what is it? Personalized medicine. Basically, it's about providing personalized drugs and with specific amounts also of drugs, which is specific to the patient. And in particular, it's useful through nanomedicine, which basically consists of engineering vehicles to deliver drugs in a particular area of our body which needs treatment, and it's released only in that area. So these are called drug delivery systems. And so this way, it's possible to minimize the drawbacks of the drugs and side effects, and to treat only the area of our body which needs treatment. So nanotechnologies in this context constitute a driving force for development, as in particular regarding nanomedicine, because nowadays it is possible to measure only milliliters of chiral. So if you want to engineer these drug-delivery systems, it is important to be able to measure much smaller volumes of the order of nanoliter, for example. So here at L'Aquila, we investigate this field of research. So we are theoretical physicists, so we study theory, but we model experiments like this on light matter interaction, light molecule interaction in optofluidic channels. Basically, these are channels where you can insert the drugs here in solution within an optical fiber which has a hollow core. So the center of the fiber is hollow. Insert your pharmaceutical inside, and you do some advanced spectroscopy, multimodal, with electric field resolution and studying circular dichroism inside this component. So the fact that drugs are confined in a tiny volume, so this is large, just to let you see it. But the core of these fibers, so the diameter is about 10 microns. So you can fill the fiber with nanoliters volume, and these are much more sensitive than standard light to the chirality of molecules. So this investigation has been recently financed by a prestigious EU project, which involves several experimental partners from all Europe and several professors from our university. I'm the coordinator, but there are several other professors from the Department of Physical and Chemical Sciences involved, also from MESVA. And as you can see, we are here on top, classified. And this is the partnership. So besides L'Aquila, there is a small Italian company called 4C Biosystems, which develops biosystems for health technologies. So there is a leading pharmaceutical company, Dr. Pharmacodynamics, is established here in L'Aquila. And there is the Polytechnic Federale del San, India, Biophotonics, IIT from Italy, which is expert in material sciences, CNRS from Nice, and the Max Planck Institute for the Science of Light from Ireland, and also the Institute of Photonic Sciences from Barcelona. So we are quite excited about this ongoing research, and as you can see, chirality, apart from dealing with mirrors, is really relevant to our daily life and to medicine. So that's it. We get out of the mirror, and I would like to thank you for your attention and hope that I didn't bore you so much. Thank you.
Okay, thanks, Andrea, for the very interesting and inspiring talk. So I want to ask people if you have questions to ask to Andrea. Please go ahead. No one? So don't be shy. Okay, I will start asking. It's just a curiosity. So it's more related to art than science or medicine. But no, because it's something that I really like. So there is also a version of the Metamorphosis of Narcissus that is by Salvatore Dali, and the strange thing in that picture, with respect to the one that you show, is that the reflection of Narcissus is not happening in the mirror, but is happening basically in the orthogonal direction of the mirror, that is the lake. And also this reflection that is not happening in the mirror itself, but let's say in nothing, is reflecting an image that is not the original one. So it's
it's an alternative universe, basically. Yes. Okay.
It's a violation of symmetry, like
or some rotational symmetry, not only. Okay.
No, it was not a not a question, but just an observation. I don't know if someone else want to ask.
I see a question in the chat from Oriana. Is separating the enantiomers very time consuming or expensive? Well, yes. So the mechanism used right now to separate enantiomers is high performance liquid chromatography. It's not super expensive right now because it is in every pharmaceutical company, but it's linked to the industrial process. So it's engineered to work with very large volumes and on continuous basis. So this way you can somehow reduce the cost of processing, but this is completely useless to develop nanomedicine. By the way, I'm not a super expert in chemistry, but separating, and so what we do here is measuring different enantiomer concentrations. But chemists are trying to develop new ways to separate enantiomers. As in particular, I think it's called organocatalysis, and they received a Nobel Prize this year for this finding. Maybe I'm not speaking well because I'm not a chemist and I'm not super expert on these new directions. Okay.
I have one question, if possible. So thank you, Andrea, for a really fantastic talk. You've mentioned throughout your talk that you are interacting with lots of different groups and lots of different companies sort of within Italy and within Europe. As a more general question, and I guess the answer is to help some of us early career researchers, is this something you think is really critical now in order to be progressing in these novel fields? Is it really important to constantly be interacting both with other academic groups and with industry? Or do you think that's just a bit of a bonus of the project you're currently working on?
Okay, so this is a difficult question. So I'm a theoretical physicist, so I'm quite far from pharmaceutical companies, but right now I'm interacting with them. But as an established academic, my impression, as I remember well when I was an early academic a few years ago, so my impression is that you just need some passion for new cutting-edge ideas and working in collaboration with other groups. Yes, it helps. Mobility it helps, from my understanding, from my experience. But not necessarily with the industry. Then of course, I came back to L'Aquila here because in this town there is some need of KTT, knowledge transfer technology. So this is more a personal attitude rather than a necessity to gather funds and to research. That's my impression. So I don't know whether this is true or not.
That's great, thank you. And one other question I had is within the realm of, obviously I understand it's confidential, a lot of what you're working on with these companies. Are you able to talk to us a little bit more about what you're working on or what the field is of that project?
Yeah, so I tried to explain it briefly in order not to get too technical. So it's basically about measuring nanoliters of chiral pharmaceuticals. They're not covered by any copyright because these are pharmaceuticals that are sold every day in pharmacies. And so this company is going to prepare several samples of these pharmaceuticals with different concentrations already measured with their state-of-the-art techniques that they use in such companies. And with all these experimental partners, we are going to apply several distinct techniques, circular degrades, also ultrafast spectroscopies, to try to tackle the measurement of sub-nanometers volume. And so the objective is to produce a nano device which can measure such small quantities and then can eventually, hopefully, benefit nanomedicine. Of course, it's clear, it's blue sky research, so it's never tried before. We think we can do that based on some theoretical predictions from us, but when you go to the lab, things might be different, you know. So let's see.
That's great. Thank you very much.
Mm-hmm.
So I don't know if there are other curiosities or question that you want to ask Andrea. Let's see if there are hands up. No.
If not, I have another more general question, if that's okay. I apologize, the naivety of my questions. I'm a biologist, so
okay.
Really interested in what you're talking about, but very naive in the subject.
Okay.
So presumably as a theoretical physicist, that means a lot of the work you're doing is modeling. Is that correct? So you're not sort of in the lab doing these experiments. Are you able to talk to us about the benefits of doing that? So presumably some of them are cost saving and time saving to be able to produce these models in advance. Is this something that has been going on a long time, or could you talk us through that a little bit?
Sure. So yeah, absolutely. So theoretical work is not so trendy right now. Not many people are doing theory, but actually it's very useful. So apart from personal interests, in my case, for example, I like the fact that doing theory, you're free from every lab. You just need a laptop. You go around the world wherever you want. You can do anything and interact with top-level laboratories from all over the world. But this is a personal attitude towards science. I like the freedom of doing that, and I like the subject. But nowadays, also large companies are interested in theory. For example, this company, Nanophotonics Univaq, they are leading other European projects, as in particular Escalate for coronavirus. It's a huge project developed, funded at the beginning of the pandemic 2 years ago. And what they do is they use and develop models to anticipate the potential effectiveness of treatments for coronavirus in this case. So this is of course helps the drug discovery, because you can just by making calculations select potential candidates for clinical trials without wasting resources in terms of time, human resources, and samples. So yeah, there's a lot of it's quite remarkable, the impact of theoretical research in terms of industrial applications.
That's brilliant. Thank you. Sorry, I was looking that way. We had our postman arrive, but I caught most of it. So that's brilliant. Thank you. And hopefully useful for everybody else too. Thanks again for a fantastic talk.
Thank you.
Okay, so again, thanks, Andrea. I think that I don't see any other question in the chat or hands-on. So I will thank you again, and maybe I hope to have you soon speaking to us to another thing, or maybe to the outcome of your project.
Let's see. Let's see. Okay. Hopefully, yes. Thank you, Francesco. Thank you, everyone. Bye bye.
Ciao, ciao, bye bye.
Thank you.
Ciao.